Hi, my name is Amitai. I'm a PhD student at Tel Aviv University, and I'll present the paper, A Lossless Deamortization for Dynamic Greedy Set Cover, written by my supervisor, Professor Shay Solomon, myself, and PhD Tianyi Zhang. So first, a bit of background on the set cover problem. So we'll start with static set cover. On the static set cover problem, we have n elements and we have m sets. Each set contains a subset of the elements, and our goal is to find the minimum size subcollection of sets that together contain all of the elements. Okay, this is in the unweighted setting. In the weighted setting, each set will have a weight or a cost associated to it, and our goal will be to minimize the total cost subcollection of sets that together contain all elements. So I'll just focus on unweighted just for the sake of simplicity in this video. So in this figure here, we have 12 elements and 6 sets. And we have frequency, which is denoted by F, and it is an upper bound to the number of sets that can contain an element. So for example, here, the frequency would be 3, since all of the elements here, they're contained in up to 3 sets. And we have the aspect ratio, which is denoted by C, and it is the ratio between the most costly set and the least costly set. So in the unweighted case, the aspect ratio would just be 1. And there are 2 classic approximation algorithms for the static set cover problem. We have a greedy algorithm that gives a ln n approximation, which will be the main focus today and in our paper as well. And there's a primal dual algorithm that gives an F approximation. And we believe that we cannot get better than a ln n approximation in sub-exponential time unless p equals np. And so in the dynamic setting, our sets will still be static. So we have m static sets. These are the colored rectangles here. And in each update step now, we'll have an element insertion or deletion. Okay. So throughout this update sequence, the maximum number of elements is going to be n, and the maximum frequency is going to be f. Okay, so some previous results, I've divided them into 2. All right, so these results here, the top 5 results, these are results that are algorithms that dynamize the primal dual algorithm. And these 2 results, they are algorithms that dynamize the greedy algorithm. Now, the reason why we need both depends on prior knowledge regarding the frequency f. So if we know that f is low, let's say lower than ln n, then we'd rather have a primal dual-based algorithm because that would give a better approximation. So we call this these results here that dynamize the primal dual algorithm. We call this the low frequency regime, where f is smaller than ln n. And we have the high frequency regime, which these 2 results are in the high frequency regime, where we have no prior knowledge regarding f. It could be larger than ln n, it could be larger than n, it could be exponential in n. So in that case, we'd rather have a greedy-based algorithm. Now, the majority of results in the minimum set covered problem are in the low frequency regime. And we see that there is one result only that gives a non-trivial worst case update time. And this update time is polylog. And we see, though, that there is no non-trivial worst case algorithm for greedy set cover. Okay, and by non-trivial, I mean anything that is sublinear. Okay, it doesn't have to be polylog, just anything sublinear. And this is actually the case even for unweighted, right? So even in the unweighted case, there isn't any known non-trivial such algorithm. So the question that we asked was, can the greedy algorithm be dynamized with a low worst case update time? Our answer to that is yes. And our main result is a result that gives the first non-trivial worst case update time. And the update time, not only is it non-trivial, it also matches the previous state-of-the-art amortized update time. Okay, and not only that, it also doesn't harm the approximation factor, okay, which is a near optimal approximation factor since we believe we can't do better than ln n. So in that sense, it is lossless. That's where the lossless in the title of the paper comes from, because we managed to get the first worst case algorithm, but with the same update time as the state-of-the-art amortized and the same approximation factor as well. And further, we were able to use the techniques from this algorithm and implement it in the low frequency regime to improve the previous state-of-the-art worst case algorithm over there. So we were able to cut off a log factor and remove the dependency on the aspect ratio. Okay, now these two results, since the set cover problem is such a fundamental covering problem that encapsulates several other covering problems in it, as direct corollaries, we were able to also reach state-of-the-art worst case algorithms for minimum vertex cover and minimum dominating set problems. All right, so the minimum vertex cover problem is just the set cover problem where f equals 2. And the minimum dominating set problem, there's a simple reduction from that to the minimum set cover problem. So we get state-of-the-art worst case update times for all of these problems. I won't get into the exact setting of the minimum vertex cover problem and the minimum dominating set problem. These are well-studied problems that I'm sure you know of. Delta here is just the maximum degree in the graph in the dominating set problem. So all of these are deterministic, and they're the best worst case algorithms now. And so I'll give a bit of a technical review with the time I have left, which is not a lot. And again, I'll only deal with the unweighted setting, since just to try to keep it simple. Okay, so static versus dynamic. So how does the static greedy algorithm work? So it works in iterations, right? So in each iteration, we have our collection of uncovered elements. And in each iteration, we choose a set that contains the maximum number of elements in this collection of uncovered elements. And then we add this set to the solution and we remove the elements from the collection of the uncovered elements. And then we continue until we're out of uncovered elements. So this is where the greediness comes from, right? We want to maximize this in every single iteration. So let's say first we chose S1 because it contains the most. So we remove it from the uncovered elements in the bottom over there. And now all of these elements, we say that they're in a set called, we call it cov S1. Okay, so cov S1, cov from cover, is a subset of S1. And it contains all of the elements that that S1 chose first. Okay, we can kind of assign these elements to S1. S1 is responsible for covering them. It was the first one that covered them. Okay, it is responsible for taking these elements out of the collection of uncovered elements. Okay, and then we do the same, continue with cov S2, S3, and S4. Now notice that all of these elements can be covered by several sets, but each one will be covered only by one cov set. And that is the set that, that is responsible for taking it out of the bank of uncovered elements, okay? So we can have this assignment of between elements and sets, right? So each element is assigned to one set and one set only. Okay. Now in the dynamic case, our goal will be to maintain a good element assignment. By good, I mean something that is that would kind of mimic the static. So ideally, what we would have is that at each and every update step, the element assignment that I have in the dynamic setting would be exactly the same as had I run the static greedy algorithm in each update step. Right? Each time I had an element insertion or deletion, had I rerun the greedy algorithm. And I would have some element assignment from that. I would want the dynamic to be exactly the same in each update step. Okay? That would obviously guarantee me an approximation factor of ln. But obviously that would be hard to guarantee, right? That in each and every update step it would be the exact same. So instead of demanding it to be exact, I'll just I'll ask for it to be similar. Okay, and how do we define now similarity? So we'll introduce this notion of levels. Okay, so we have these levels. We have beta, which is a number larger than 1. And let's say cov S2, for instance, we will place it at level 3. we want it to be at level 3 if its size is between beta to the power of 3 to beta to the power of 4. Okay, so we have these kind of like buckets or levels. And in the static case, so this is some kind of a discretization or relaxation, where in a static case now, how it would work is instead of in each iteration choosing a set that maximizes the number of uncovered elements, what we would do is kind of, since we're making it discrete, then we can start, let's say, at the highest level. Let's say it's beta to the power of 10. So we ask, is there any set that contains more than beta to the power of 10 elements in the collection of uncovered elements? If the answer is no, then we ask now for beta to the power of 9. And let's say the beta to the power of 9, there are several. So I say, all right, just give me one of them. Doesn't matter which one, give me one of them, add that set to the solution and remove the elements from the uncovered elements. And then ask again, are there any more in beta to the power of 9? And then I continue and so on, and then I go to beta to the power of 8 until I reach the bottom. Now it should be quite trivial that this would give, instead of a ln approximation, a beta times ln approximation, just because of this relaxation. But this relaxation is necessary for the update time to not blow up. All right. So now in the dynamic case, what I want to do is to maintain this level structure throughout. So each element will be covered at a level, and each set will be covering at a level. And I want to maintain this this kind of assignment. But what the two most important things I need are in the ideal guarantee here. The first one is that each cov set is indeed in its appropriate level, meaning if cov is 2, if its size is between beta to the power of 3 to beta to the power of 4, I want it to really be in level 3. Okay. Obviously, this can change because the cov set can grow, can shrink due to insertions, deletions. But that would be part of the ideal guarantee. And the second part is that there's no cov set that can be created by taking elements and raising their level, meaning elements are as high as possible. The equivalent to this in the static is that elements are chosen as early as possible, right? If I can consider an element here that's in S1, in cov S1 too, and let's say that it's also in S3, but I want it to be in cov S1, not in cov S3, because cov S1 is at a higher level. Okay, just like in the static, I want to choose the elements as early as possible, right? I start from the highest level when I choose them, and then I go lower and lower, right? As in the example I said earlier, I start with level 10, and then I go to level 9, and that's the order that I choose them in. That's the greediness. So here also, I want elements, their level to be as high as possible, okay? So if I can guarantee these two, then I will have a beta times ln approximation factor, okay? And insertions, what do I do? Once I insert an element, it has up to f sets that can contain it. And I just check which one is at the highest level, right? So that I'll still obey the ideal guarantee. So let's say that this element belongs to S1, S2, S3, and S4. I'll make it join cov S1 though, since cov S1 is at the highest level. And in deletion, all I do is just remove from the cov set. So that's pretty much the algorithm. I have insertions, I have deletions, I have rises, which when I want to create a new cov set at a higher level, that's what I do so that I can still obey the ideal guarantee. And also falls the other way, so that I could still obey the ideal guarantee. Now, this algorithm is what we call a local algorithm, in the sense that the invariants are very local, right? They have to apply to each and every set. Okay, so by locality, I mean to each and every set. Okay, each and every set, if it needs to lower its level, then it must lower. If it needs to raise its level, then it must rise. So it's kind of a very strict invariant that has to apply for each and every set. And I just need this so that I can use the same approximation arguments to show that I have a beta times ln approximation factor. Now, the previous algorithms in the high frequency regime, they are all to some extent local algorithms, okay? So I won't really get into now the update time analysis and all of that, but let's just assume that we can, from this local algorithm, we can get a good amortized update time. But it's only amortized update time. It's not necessarily worst case, because at a certain point, I'll have rises and falls. And these could be rises and falls of several elements. So if I have a rise or a fall of several elements, that means I need to change the level of all of these elements. And changing the level of all of these elements will take time linear in the number of elements there are, right? Because I need to update the level of each and every one of them. So that's the problem when I want to now deamortize it. Okay, so if I want to now deamortize a local algorithm, so I would have to simulate falls and rises with a delay. By simulate, I mean maybe having it in the background, computing it, but it has to be over several update steps, right? I have to it's kind of a slow execution because I don't want the worst case update time to blow up. So I kind of need to delay this this rise or fall to occur, and that's a problem because let's say, for example, I have the set S, and I have all of these elements that now are in S, and they want to create some covariance at a higher level by raising the level of all of these elements. This takes a lot of time, though. Now in the where I don't want the worst case update time to blow up. Okay, so I need to wait for this execution. It could take several update steps. Now, during these update steps, other things happen, right? I can have maybe several falls of these elements, and now they can drop to a lower level, and they can now join this set that also wants to climb. So now this set that wants to climb, now it can extremely violate the ideal guarantee, and this could immediately blow up the approximation factor. Okay, so I won't explain exactly how it blows up the approximation factor, but I hope that this example does give some intuition regarding that. So it can completely blow it up, which is bad. So this local algorithm is problematic if we want to deamortize it, because these rises and falls have to occur instantly. So what we need to do is we need to obtain a global amortized algorithm and deamortize it. Okay, now what do I mean by a global algorithm? So we don't want to allow any more rises or falls for specific sets. Okay, so we kind of want to relax our ideal guarantee so that it will hold in more of maybe an average sense. So maybe there are some sets, a minority of sets that that can violate the ideal guarantee, as long as the vast majority do not, and they're okay. Okay, so this demands something completely different. And then, like I said, again, we have to deamortize it. Okay, so there are two challenges here. So when we want to obtain a global amortized algorithm, we have three objectives. Okay, so we first need to define some kind of global notion of dirt. Okay, so this is kind of some kind of global measure that determines how far we are from the ideal guarantee. But it must hold in kind of an average sense, all right? So we need that. And then we need to define a global algorithm corresponding to this global notion of dirt, meaning once we have enough dirt, we need to clean up the system somehow, okay? And without local changes, something a bit more than something more global. And lastly, which is also the hardest part, is we need an inherently different approximation factor analysis now, right? Since we can't assume that each and every set the ideal guarantee holds for it, we need a completely different approximation factor analysis, which was one of the more non-trivial parts of our paper, which obviously due to time constraints I won't get into. So that's just the first challenge of obtaining a global amortized algorithm. And next, also, I won't have time to discuss, though, the second challenge, which is the efficient lossless deamortization process. All right, so some future problems. First one is extending these techniques to other problems. So like I said, we did this only for the set cover problem, but the set cover problem contains other important covering problems like the vertex cover problem, minimum dominating set, minimum edge cover problems. But we haven't tried this to see if it maybe works. We can implement it on completely different problems. The efficient deamortization, the lossless deamortization. And another thing was to see if we can optimize maybe the running time, right? So now it's f log n, but maybe we can ideally lower it to order f but maybe improve our F log n time, that would also be good. That's it. Thank you very much for your time. Appreciate it.